everyone. Today's topic is tertiary butyl hydroperoxide and peracids. So we'll be dealing with the oxidations topic. Okay. So in the reaction, what happens here is we are taking the cyclopentanol, or when the cyclopentanol is treated with the tertiary butyl peroxide, it's in the presence of vanadilyl acetyl acetone. On here there is, you can write this compound as this bond will be little bit tilted, so that you will get back this structure. This structure is similar to this. So here what happens here is the oxygen will go and bind with this reagent, and there is a formation of this reagent. Okay, there is a formation of this complex moiety. Once the complex moiety is formed, that time this alkene will go and abstract the proton. Meanwhile, there is a cleavage of this tertiary butoxide, right? And then there is a cleavage of the tertiary butoxide, right? And then this vanadilyl compound gets cleaved out. So there is a generation of one of the negative charge. This bond shifts and there is a generation of the positive charge over here, which will abstract the proton. You will get back this structure. That is here, if you will see, just the alkene is epoxidizing. Okay, and the alkene is getting epoxidizing, and you are getting this structure. All right. So moving on to the next point, if you will take the vanadilyl acetyl acetone, so what happens here is, one second, okay. So here vanadilyl acetyl acetone is the square pyramidal complex. Okay, which will have the two molecules of the enolate of acetyl acetone and vanadilyl compound will be present. So that can easily accept the another ligand to form the octahedral complex. This can accept the ligands to form the octahedral complexes. And henceforth what happens here is, when this forms the octahedral complex, there is a plenty of an alcohol which can be added, and for the tertiary butyl hydroperoxides to displace one of the acetone ligand. Okay, one of the tertiary butyl hydroxyl group, tertiary butyl hydroperoxide, will be replaced by one of the ligand like ACAC. That is your acetyl acetone. Okay, so moving on to next slide, that is your peracids or peroxy acids. So this is your peracids structure. Okay, that can either be called it as the peroxy acid. So here, moving on to preparation part, like how it can be basically prepared. Basically, how the peracids are prepared is we are taking the carboxylic acid. On treatment of the carboxylic acid to the hydrogen peroxide, it will produce the carboxylic peracids with the cleavage of your water molecule. If you will see here, one of the oxygen atom is getting added up to the carboxylic acid, and you are getting the peracid. Okay, moving on to preparation. And so here there are certain preparation, and that is your trifluoroacetic acid. So if you will see the structure of trifluoroacetic acid, this is your trifluoroacetic acid structure. So this is your trifluoroperacid structure. Okay, so here you are taking the trifluoro acid, and then upon treatment with the hydrogen peroxide, you are resulting in the trifluoroacetic acid with the cleavage of your water molecule. And then moving on to second preparation, it is your metachloroperbenzoic acid. This M should not be in caps, just maintain this one. The M should always be in small. Okay, right, make it as the small m. MCPBA. This is a small m, and then So if we are taking the chlorobenzoyl chloride, right, so when the chlorobenzoyl chloride is treated it with the NaOH upon treatment with the hydrogen peroxide at 25 degrees Celsius is with MgSO4, at that time you will get the perbenzoic metachloroperbenzoic acid. Okay, so first there is a formation of the salt, that is your when you are treating it with the Na, there is a salt formation. So moving on to the next slide, and then it will abstract the proton and there is a generation of the compound. And then if we are treating it with the hydrogen peroxide upon treatment with the base is, that is your alkali, what happens here is again there is a cleavage over here. When this bond gets cleaved out, that time the one of the OH will come and bind over here, and then the another O minus will come and sits over here. Okay, so what happens here is first there is a salt formation and followed by the formation of your peracids. Okay, so in this reaction first there is a formation of your monoperphthalic acid. Once the monoperphthalic acid is formed, and if we will do the hydrolysis, that if we will add the H plus, at that time the Na plus will cleaved out by the formation of your peracids. And then moving on to next, if we are taking the peracids can also oxidize the alkenes to the epoxides. So when an alkene is treated with the peracid, the epoxide is formed with the cleavage of your carboxylic acid. Alright, then moving on to mechanism part. In the mechanism, what happens here is the reaction will takes place by the transfer of the oxygen atom. Okay, from the peracid we are taking the peracid and then we are transferring the oxygen atom. Alright, to form an we are taking the starting material as an alkane and then we are taking the peracid as our reagent, and when the peracid oxygen is added up to an alkene, there is a formation of an epoxides, that is your epoxidation reaction. Okay, so remember this step, that is your this reaction will involve only one step process. Okay, single step process is there without the formation of any of the intermediates. Okay, and then the epoxidation is stereospecific, leading to the syn addition of the oxygen atom. Okay, there is a syn addition of the oxygen atom over here. So if you will take the nucleophile such as an alkene and here the electrophile is your peroxy acids. So here what happens, the alkene bond will go and attack the oxygen atom. Meanwhile, this one bond of the peroxy acids between the two oxygen atoms will just go shift over here, make it as a double bond. This bond again shifts. This bond again shifts, and then when this bond shifts, at that time you will get a negative charge. By having two bonds, that is when the two bonds are present, at that time it will not give you a minus charge. Okay, so when this bond shifts, then you will get the minus charge, and then it will abstract the proton. This bond will cleave out, resulting you in the epoxide formation. And then with the cleavage of one of your carboxylic acid from here, you are resulting in the epoxide formation. Okay, this is a mechanism part. Then certain things in the mechanism is so what are the conclusion by this mechanism? So we can conclude that the rate of the epoxidation will be increased by the presence of the electron withdrawing groups in the peroxy acids. If we are taking the peroxy acid, if we are substituting the R group of your peroxy acid with an electron withdrawing group, okay, at that time the rate of the reaction will be increased. If it is an electron donating substituents, at that time also it can happen, the rate of reaction can increase is if the alkene has the electron donating substituent. Okay, if the alkene will have the electron donating substituents, and that time the electron donating substituents, that time the rate of the epoxidation might increase. Okay, and then terminal alkenes will react very slowly with the peracids compared to the alkyl substituted alkenes. This is the reactivity of the olefins. Please go through this one. And then electrophilic reagent. So the peracid reactivity. What is the peracid reactivity? Alright, so at the carbonyl carbon of the peracid, if you will see the carbonyl carbon of the peracid, the presence of the electron withdrawing group, that the R will be present over here. Okay, if suppose just try to avoid this one, the CF3, and then if you are considering it as an R group. Okay, so if the R group at the carbonyl of your peracid, the presence of the electron withdrawing group will increase the reactivity of your peracid, that is you are taking the trifluoro or peracids, and then which is highly reactive species. Okay, and then moving on to the next slide, it is your, although the trifluoro or peracid is highly reactive in epoxidation, it is less commonly used for the synthesis purpose. It is rarely used. Though it is highly reactive, it is not it is not easily available. Okay, and it is very expensive, and then it is highly unstable compound, highly reactive but it is an unstable compound. On the byproduct of the trifluorocarboxylic acid will open the epoxide formation. Okay, and then moving on to regioselectivity, regioselectivity in the epoxidations with the peracids. So which region you have to select, whether the alkene of this terminal alkene or this less substituted alkene or the more substituted alkene, which region you have to do the epoxidation formation, right? So here if you will go through the first point, that is in the olefinic compound which is having the multiple double bonds. Okay, the selective epoxidation will take place at the highly alkylated a double bond. So here if you will see, the highly alkylated double bond is this one. So what happens when we'll add the peracid, that time the epoxidation will take place over here, not towards this terminal alkene. Okay, because here it is highly substituted molecule, that is it is like a historically hindered site. Okay, so whenever there is this case is regioselectivity of the olefinic compounds, the double bond and epoxidation will take place with the highly substituted compound. And then moving on to next reaction, here if you will see, we are taking the diene compound, and then if we are treating with the peracid and in presence of the dichloromethane, and there is a two product formation. One, it can be either take place with the highly substituted alkene, and the another one where it is a less substituted alkene. So in the first product you will get the major one, which is your highly substituted, and the minor one will be your least substituted, that is this alkene will get affected. Okay, moving on to third reaction, if you will take this as a substrate, if you treat it with the peracid, so what happens here is this alkene is getting affected. Okay, not this. Okay, then moving on to next slide. In this reaction, this all are like application part. Okay, so you can apply all these regioselective reactions with the in the application part. It can be given for the predictive product for your exam point of view. So if you are taking this as your substrate, that time you can see here it is getting affected. This alkene is getting epoxidized, and here again this alkene is getting epoxidized. Okay, then moving on to the next point, it is the conjugated olefins are weak nucleophiles than the isolated olefins. Alright, so remember, the conjugated olefins are weak nucleophiles than the isolated olefins. So if the compound contains both the selective epoxidation, if the compound contains both, it can be the both of them, that is your conjugated as well as your or isolated olefins. That time what happens, the selective epoxidation will take place at the isolated olefin molecules. Okay, so if you olefin ring, that is if you are taking this starting material, if you are treating it with the MCPBA, that is your metachloroperbenzoic acid, so this part of your alkene is getting affected irrespective of this alkenes. Okay, and then moving on to next point, again this part is getting affected rather than this side, and then in the presence of your benzene you are doing this reaction. Stereoselectivity, there I have spoke about regioselectivity is over, and then selective epoxidation is over, and then stereoselectivity in epoxidation with the peracids. So here what happens here is, what is the stereoselective reaction? In the chemical reaction, if the stereoisomers will be produced in the unequal amount, if the unequal amount of the stereoisomers are produced, that reaction is known as your stereoselective reaction. Okay, it is based on the stereochemistry of the compounds. So in this point, so what happens here is the epoxidation at the olefin is in addition, and henceforth it depends on the spatial selectivity. Therefore, whatever the stereoselective reaction is there, that will depend on the spatial selectivity. There are two phases, right? Like it can be a front attack or as the back attack. So here there are two phases where the oxygen atom could be donated, that is your back and front phase will be there. If there is an alkyl substituent at the double bond approaching the reagent, preferentially it will deliver the oxygen at the sterically less crowded site. Okay, so if you are taking this compound and upon treatment with the MCPBA, what happens here is this epoxidation is taking from the back side, and then your back side, whatever the epoxidation is taking place is, that is your major product, and this is your minor product. And then if you will see here, upon treatment with the this one toluene, not the toluene one, and so cyclohexatoluene. In so if you will take this compound on, again what happens upon treatment with the MCPBA, this alkene is getting affected with the epoxidation, that is you are doing the back attack, and then again here also you are doing the back attack in the presence of MCPBA. So moving on to chelation or hydrogen bonding. What is the chelation or hydrogen bonding? So here in this, at the allylic position, and at the allylic position, if there is a chelating group such as the amino group NH2 or OH, as the epoxidation is preferentially takes place at the same side of the chelating group. Okay, it will takes place, epoxidation will takes place at the same side of the chelating group at the allylic position. So here steric crowding will be suppressed by chelation compound. When we'll add the chelating compound, at that time steric crowding will get suppressed as between the group at the allylic position and the approaching reagent. Like if you are taking this one, this is your allylic compound, and then this is your reagent, that is your hydrogen peroxide. So with this it is getting suppressed, and then there is a formation of an epoxides. Okay, so here the group at the allylic position will develop the hydrogen bonding with the reagent and hold spatially at one phase of the olefin. So it will hold only one phase of the olefin. Okay, it will not go here and there, it will hold only one phase. So here the cyclic systems are the best examples. So we are taking the cyclohexanol compound, and then if we are treating it with the peracid, so what happens here is we are resulting in the two products. One is if there is a front attack, at that time you will result in the major product. If it is back attack, it is your minor product. In the chelation, this and all will takes place, whereas in the previous slide which I have shown, on the back attack is acting as the major product. Okay, so and then again if you are taking the cyclohexanol, this is can also be similarly written as in this form. When the attack, we are showing the attack over here. When this attacks will takes place, this is your peracid. Okay, this oxygen will have one bond with the hydrogen. So here this can be written as in this form, right? Cyclic structure. So if you will see here, this, if it will open, the carbon atom is of 4 valency. One is attached with the OH, that is your this part, and then again the H atom. So here what happens here is, the attack is taking place via like this. is this bond shifts, it will take the oxygen atom. Meanwhile, the bond which is present over here, right, and this bond again takes the hydrogen atom. Okay, and then there is a cleavage of this group, and then you are getting back this adduct formation. And when this adduct is formed, this is your like an intermediate formation is taking place. See the arrows properly. Okay, so once this arrow is taking the oxygen atom, again the carbonyl compound will take the hydrogen and it is forming one of the first this will take this hydrogen, and then there is a formation of one of the like dash bond over here. Okay, it is not forming a perfect bond but just it is showing like that. And then after the formation of like an intermediate, this whole moiety will get cleaved out, that is your RCOOH will get cleaved out, resulting you in the epoxide formation. Okay, so after the formation of an epoxide, after the formation of an epoxide, so what happens here is this can also be written it as in this form, right? This is your OH will not go anywhere. Okay, so here are certain examples, please go through this one. In general I will speak it about. So here alkene is getting epoxide, so you can see here again here also alkene is getting epoxide, and again you are getting this epoxide formation when and the alkene is getting epoxidized. It can also be act as by sterically if you are taking the endosterically crowded compound. In this reaction you are taking the cycloaminol. This will be favored for an exosterically favored, resulting it with the epoxidized formation. This is an endo compound. So what happens here is there are two there are two product formation, that is one is your major product and one is your or minor product. So here if you are treating it with the peracids, this product is your major, or if you are taking the endosterically crowded, if you are taking the exosterically crowded compound, that time endo is your major, exo is your minor. Okay, so here it is an exo is your major compound and endo is your minor compound. And if you are taking these endosterically crowded compounds, if you are taking the same compound and then upon treatment with this, if you are taking the exosterically favored compound, that time you are getting these two products. Then moving on to limitation part, there are a few limitations. One is the peracids are inefficient in the epoxidation of your conjugated olefins. And so here if you will see the terminal alkenes are getting affected, and here we are getting the very less yield upon treatment with the chloroform. Okay, and then that is one of the limitation. And in few cases what happens, if we are taking the alpha beta unsaturated alkenes olefins, in upon epoxidation of the peracids, that is your BV oxidation, that is your Baeyer-Wilger oxidation, and that is your side competitive reaction. Okay, so here what happens here is the two products is formed again. One is your epoxide formation will be there, and in one more reaction what happens here is there is just an addition of the oxygen atom. Okay, that is also will come in the limitation part. So moving on to the third limitation, when an inefficient in epoxidizing of the terminal alkenes because of the low nucleophilicity, that will be the one more limitation. And then moving on to Des-Martin oxidation, and here in the Des-Martin's oxidation what happens here is we are taking the high valent iodine compound on the high valent iodine compound, which is known as the Des-Martin periodinane. Okay, remember this. Des-Martin oxidation means you are taking the high valent iodine compound which is known as the Des-Martin periodinane. This is an important reaction for an exam point of view, and for the CSIR net and all, you will get this type of questions. So which is a mild oxidizing agent, which is used to oxidize the very sensitive alcohols to the carbonyl compound. Suppose if you are taking the OH groups, that will reduce to your carbonyl compound. That is the main criteria of this. It will oxidize this one. If you are taking the DMP is nothing but it is your desmartin per iodinane. This is the structure of your or desmartin per iodinane. Okay, so this is not a reaction. This is just an arrow to show this compound, that is your iodine in 5 hypervalent compound. Okay, and then moving on to preparation part, how will synthesize this desmartin in per iodinane is we are taking the iodobenzoic acid and then we are treating it with the KBrO3. If we are treating it with the potassium bromate, what happens here is the one of the cyclic structure that is formed between this one, that is very explosive when it is dry, so it will be in the moist condition itself. Else upon treatment with the acetic anhydride, and then again this complex is generated, that is your or heptavalent compound. Okay, that is your hypervalent compound, DMP. Moving on to next, in the uses you can see we are taking an alcohol, upon treatment with the DMP we are resulting in the carbonyl compound. Here we are taking RCH2OH, so it is resulting the RCHO, primary alcohol to the aldehyde. Right. And then in the mechanism part you can see if we are taking the primary alcohol upon treatment with the DMP, so first what happens here is the oxygen which is having a lone pair of electron will go attack to the iodine atom, iodine, and then meanwhile one of the OAC minus will get cleaved out. When this OAC minus will get cleaved out, that time what will result is the oxonium ion is generated, that is the oxygen will gain a positive charge and the OAC minus will abstract the proton. Meanwhile the cleavage, this bond will neutralize the positive charge. When this bond will neutralize the positive charge, you are resulting in this adduct formation. And so again what happens, one more molecule of your ACOH, that is your acetic acid, is getting cleaved out. So this when this OAC minus will go, it will OAC minus will abstract the proton, that is your intramolecular reaction, and this bond shifts over here and then it will make a double bond on, and then this again bond shifts over here and you will get back your or aldehyde compound by the cleavage of your this moiety. Okay, that is your minor product. Thank you. If you have any doubts, you can ask me in the comment box.